I will kind of start from where I left off yesterday. So we got to the point where we were talking about large n equals 4, large n equals 4. S3 cross S1, where this S1 is the temperature direction, and we are thinking of this as a Euclidean partition function of this theory on S3 cross S1. And we pointed out that at strong coupling, lambda tending to infinity, the theory exhibits a first order deconfinement transition, which is also known, of course, as the Hawking-Page transition between thermal AdS and the big Schwarzschild black hole geometry. For lambda much less than 1, we very quickly summarize that actually this picture of deconfinement continues to hold. In fact, it continues to hold even when the theory is in the free limit. So let me just quickly sketch what was the basic idea there. So one thing that we pointed out yesterday is that even the free n equals 4 theory at large n, when you study it on the sphere, has a Hagedorn, has at least a Hagedorn growth of states. And that tells you that there will be a critical temperature where there's something non-trivial that happens. In order to understand what actually happens, the most systematic way to compute the partition function at weak coupling is to calculate the partition function systematically. What you need to do, and what was realized by the people who wrote this paper with a lot of, with about 6 authors, Aharoni, Marsanoni, Bala, Papadodimas, and Van Ramstok, so that's around 2003, is that the right way to think about this problem is to actually think about it in the Wilsonian sense. Which means that you want to keep the lightest mode, so to speak, and then integrate out all the heavy modes. And that's something that we can do very naturally because we are on S3 cross S1, and all fields can be decomposed in some Kaluza-Klein harmonics of S3 cross S1, momentum harmonics of S3 cross S1. And what you need to do is to basically keep the one mode which has a zero mode on S3 cross S1. So that, and integrate everything out and get an effective action for that one mode. Now there's actually one, if you look at all the fields in the n equals 4 theory, there's only one mode which actually has a zero mode. So potentially n equals 4 theory has 6 scalars. I goes from 1 to 6, but when you put a conformal field theory on a compact space like an S3, there is only one consistent way in order to couple the fields of that theory to the curvature of the background. In fact, you are forced by conformal invariance to introduce a coupling for these scalars to the curvature of S3. That's just dictated by conformal invariance. So these scalars, by conformal invariance, in fact, it's something that you can just deduce by starting from n equals 4 theory on flat space and then just doing a conformal transformation that maps flat space to S3 cross R, and you will find that doing that conformal transformation actually induces a non-zero effective mass term for these scalars, okay, at the tree-level Lagrange. So this is standard in whenever you study quantum field theories and curved space-times. There's the possibility that the scalar fields in that theory can obtain a mass by coupling to the background curvature of the space. So by conformal invariance, these scalars have a mass given by 1 over the radius squared of the S3. And in all that follows, I'm setting the radius of the S3 to 1. So the point is that due to conformal invariance, the scalars have a mass, have a bare mass in the free-level Lagrangian when you write the theory down on S3 cross S1. So the scalars do not have zero modes. Okay, the lightest mode of a scalar field, even though it might be a zero momentum state on S3 cross S1, still has a non-zero mass because of this 1 over r squared. And then the fermions, and as you might expect, the transverse gauge fields, physical gauge fields, of course, do not have zero modes because they have so these do not have, these are not the lightest modes. So even the zero momentum modes of the scalars are not light because they have a bare mass term. The gauge fields and the fermions, okay, they do not have zero modes. Okay, they do not have zero modes, which means that if you do the Kaluza-Klein decomposition or the momentum decomposition of these guys on S3 cross S1, you will find that they all have non-zero harmonics. Okay, so that means these are all heavy fields and they need to be integrated out. The only object that actually has a zero mode which is the lightest field, is actually A0. Okay, normally you might want to say that A0 is not a physical degree of freedom, but actually in this case it is a degree of freedom that you cannot completely gauge away. So you would normally think that you can set A0 to 0 by a gauge choice, but this cannot be completely gauged away. Because the time circle is compact. Time direction is compact. And there is a possibility that this object there's a possibility for introducing a zero mode or a holonomy, a non-zero holonomy for the gauge field around this time circle. So that's, if you have a non-zero holonomy of the gauge field around this time circle, you will never be able to gauge it away. It's like a web, it's a Wilson loop. It's a web for this Wilson loop. So you cannot gauge it away if it's non-zero, and you have to allow for the possibility that it's non-zero. It may be that dynamically it is set to 0, but you cannot a priori set it to 0. So you have to allow for the possibility that this guy gets a web, and this object has zero momentum mode on S3. So what you should actually do is introduce the order parameter. So which is very closely related to the Polyakov loop. The order parameter that we will be interested in would be defined as this n by n matrix alpha, okay, which is given by the integral of A0 over the time circle, and this still has some spatial dependence. So you want to extract the lightest mode. So you want to take the spatial average of this guy over S3, and just to normalize it, divide it by the volume of S3 and beta. But you may or may not actually let's leave it like that. So this object, if I exponentiate, so this is of course an n by n matrix in general. If I exponentiate it, it's not exactly the Polyakov loop, but it's very closely related to the Polyakov loop. It's e to the I of the zero mode of A0. Okay? It's very closely related to the Polyakov loop. So let's actually just, loosely speaking, call this the Polyakov loop. In fact, this is not the Polyakov loop, this is the holonomy matrix. So let's call this a unitary matrix U. And the Polyakov loop would be 1 over n times trace of u. Okay. And of course, you can consider you can consider traces of arbitrary powers of this unitary matrix U. So actually, all the information about this unitary matrix is contained in the Polyakov loop, but also in more general traces. So you can define more general traces of this object, like so. And if you can calculate all these powers, traces of all these powers, you also have information about this full matrix, this n by n matrix. Equivalently, all the information about this matrix can be contained in the eigenvalues of this matrix. So it's most useful to actually view this system in terms of in a gauge where this matrix U is diagonal. So you can make a gauge choice okay, and then because this matrix is unitary, you have to have summation of alpha I is equal to 0 mod 2 pi. Okay. So you can make this gauge choice, but the point is that this is the zero mode of the theory. This is the only object in the theory that has a zero mode. All other fields have harmonics. So you can integrate everything out and get a partition function that can be written as an integral, as a path integral, or actually at the end of the day it's just a matrix integral, because we have lost space-time upon doing the Kaluza-Klein or harmonic decomposition, and so the partition function just becomes an integral over this unitary matrix with some effective action. Okay, so this effective action I will just write down its general form, which is pretty much dictated just by the fact that the action has to be gauge invariant, and the fact that the action is Zn invariant. Okay, so these two facts actually tell, and the fact that we are working in a free theory completely constrains the form of the action to be of this form. But these are just some coefficients which depend on temperature, and then you have trace okay. So the fact that you get you get only two powers. So this is what I call little u. What do I call these things? Okay, u and dagger. Okay, so the fact that we only get bilinears in u has to do with the fact that we are dealing with a Gaussian theory, which means that we are looking at a theory in the free limit. The fact that you get products of these two traces, u to the m and u dagger to the m, is dictated by Zn invariance. Okay, so Zn symmetry, which is the center symmetry, corresponds to large gauge transformations, which means gauge transformations that don't come back to themselves when they wind around the time circle, but only come back to themselves up to a phase factor which lives inside Zn. Okay, so if you do a Zn phase transformation or a Zn gauge transformation, a large gauge transformation, you'll find that each of these guys individually gets multiplied by a phase. And the fact that you have only these combinations, trace u to the m and trace u dagger to the m, means that whatever phase factor you get here is cancelled by that guy. So this is Zn invariant. So this is dictated by Zn invariance. And the fact that this is a Zn invariant action has to do with the fact that the original theory that we started with, n equals 4 theory, has only adjoint fields in its spec, in its microscopic definition. So in fact, if you did this calculation for just ordinary Yang-Mills theory or just n equals 1 supersymmetric Yang-Mills theory on S3 cross S1, you will get the same result. same form of result. So you take ordinary Yang-Mills theory and assume that the three sphere is sufficiently small so that the gauge coupling can be taken to be arbitrarily small by asymptotic freedom, right? And then you could just write the partition function in the free or Gaussian limit for this effective matrix U, which is this holonomy matrix, and you would find that it has to have this form. Okay, so so you get this effective action, which is pretty much dictated by William-Waves, and you can, I mean, these coefficients are very easy to compute, and you can actually get it explicitly. The key point is that rather than writing down what happens to these coefficients, let me just mention that the first coefficient, which is A1 of t, okay, this is positive. In fact, all coefficients tend to be positive as long as the temperature is less than this particular number. So as long as the temperature is less than that number, okay, it turns out that all these coefficients are positive. And precisely when the temperature becomes bigger than this, A1 of t becomes less than 0. Okay. This number just is dependent upon what the particle content of the theory is. How many scalars, how many vectors, and how many fermions the theory has. If you study pure Yang-Mills theory, you will find a slightly different looking number. Okay. But it just is something that you can get. These coefficients, AMs of T's, are just determined by single particle partition functions, okay, of fermions, bosons, and vector particles on S3. It's just a technical thing to compute. So this A1 is bigger than this. So that means that, so let's call this some T critical. So for T greater than T critical, A1 of T changes sign. And if it changes sign, this piece here is like a potential energy term, right, for U1. U1 is actually nothing but what we call the Polyakov loop. It's the first trace. So that means that at this critical temperature, one of these trace modes, which is actually exactly the Polyakov loop, the first trace, it has a negative mass square. So that means it wants to condense, right? And in fact, if you plot this effective potential just for the first trace, which is the Polyakov loop, the other traces are Polyakov loops and are multiple Polyakov loops. So if you plot this effective potential, V effective versus the first trace, then for T greater than T less than Tc, it's just monotonically increasing with minimum at U1 equals 0. And the important point to remember is that the max U1, which is the trace of a unitary matrix divided by n, cannot have an arbitrary value. It has a maximum value. In fact, it's bounded by 1. It cannot be bigger than 1. So the space of configurations is bounded here. So that's T less than Tc. For T greater than Tc, this potential just does that, and then the expectation value of the Polyakov loop is bound to be that 1. Okay, so it's a kind of transition between a phase where U1 is 0 and a phase where U1 is 1. So Polyakov loop is 0 here and Polyakov loop is 1 here. That's deconfinement. And I won't belabor this point here, but let me just mention a couple more things here, which is that you can view this transition from the point of view of what happens to the eigenvalues of this unitary matrix, and that's so in the eigenvalue basis, where this unitary matrix is written in terms of those phases, you can rewrite the partition function in terms of an integral over these eigenvalues, and there is a Jacobian that you get when you go from the unitary matrix to the eigenvalue basis. So that's a well-known fact that when you go to this Jacobian, you get is this famous, well, it's actually the analog of doing Faddeev-Popov gauge fixing, but for matrix models. But if you do that, you will find that you get a Jacobian, which is the famous van der Monde determinant. And for unitary matrices, it takes this form. Excuse me, I don't think I want to write it like this. Sorry. What I meant was that it's exponential. And then minus S effective. So the effective action there, which we have here, we can rewrite it in terms of eigenvalues. But in addition to the effective action we already have, we also need to supplement it with this Jacobian term when you want to think of this integral as an integral over eigenvalues as opposed to the unitary matrix. And a little bit of thought will convince us that both these terms scale as n squared, because this is a sum over, this is a double sum over n eigenvalues. So this is an order n squared term. This is order n squared. The effective action is also order n squared. So both these terms actually compete against each other. And what this is trying to do, this Jacobian term actually acts as a repulsive potential or a repulsive force between the eigenvalues, because if eigenvalues try to come together, the sign goes to 0 and the log of 0 is minus infinity, so that is disfavor. So the eigenvalues want to be away from each other, so that's a repulsive force. So this is a repulsive eigenvalue interaction. And the effective action actually wants to, if you write the action in terms of the eigenvalues, you can convince yourself that the effective action wants to do the opposite. It wants to attract the eigenvalue. So there is a competition between these two. So at low temperatures, what happens that an alternative way to view what's happening here is that for T less than this Tc, actually it's the repulsive interaction that dominates, which is the eigenvalue repulsion. And because the repulsive interaction dominates and all the eigenvalues are valued on the circle, because these are phases, the eigenvalues just spread themselves uniformly around the circle. So in the large n limit, the density, eigenvalue density, as n goes to infinity, you can introduce a density function for the eigenvalues, rho of alpha. Alpha goes from 0 to 2 pi, okay, because that's the eigenvalues are valued in a circle. So for t less than Tc, the eigenvalue density is just uniform, because these eigenvalues want to be uniformly spread on the circle. So that's a uniform distribution. And then what happens for t greater than Tc is that this eigenvalue distribution between 0 and 2 pi actually develops a gap. So that's a gapped distribution. And then you can easily convince yourself that if you have a uniform distribution of these phases, the trace of the Polyakov loop matrix, which is just the sum of these eigenvalues, has to be 0. because it's uniformly distributed. If it's gapped, then it's centered around some non-trivial value, and then if you take again trace or sum of e to the I alpha, sum over all these eigenvalues, you get a non-zero result. So you get a non-zero Polyakov loop. So the key point to remember is that deconfinement is associated with a uniform distribution of eigenvalues of the Polyakov loop going to a non-uniform distribution, in particular gapping of the eigenvalue. So there is a bit more information in this eigenvalue distribution than there is, or there is a lot more information actually in the eigenvalue distribution than there is only in the Polyakov loop. So the Polyakov loop is just the first trace, and you could compute multiple Polyakov loops, in other words, multiple traces of the holonomy matrix, and all that information is contained in this. There's a much richer structure which is associated, there's much richer variety of possibilities that is associated with what happens when you consider the theory at finite coupling. And I was briefly alluding to this yesterday, and I don't want to spend too much time.
Right.
But yes.
How do you see that profile from previous discussion?
Well, you just have to solve for what you have to do is, I mean, it's a little bit of work. You have to introduce the density function, take the large n limit of these equations, and then there's a saddle point. There's a saddle, because there's a large n, it's a large n integral. It's dominated by the saddle point. So then you write down the saddle point equations, and from that you deduce this rho of alpha. The fact that it has a gap, I think that more or less, I mean, the fact that it has to be non-uniform is clear, because only if it's non-uniform you're going to get a non-zero expectation value for this guy. The fact that it's gapped, maybe it's less easier for me to explain just without doing the calculation.
Is there an easy way to see that it's peak at the high?
I think that's just a choice of, we just made a choice. In fact, yeah, it doesn't matter where it's peaked. The choice that we've made is that, in fact, we made this choice that sum over alpha I is equal to 0 mod 2 pi. So maybe I should have actually drawn this distribution between minus pi and plus pi. Maybe that would have been more appropriate. Yeah, the center of mass doesn't really matter. It just changes all your results by an overall phase. Right. Started at 2. Okay, so maybe for this, all I'll say is that even at weak coupling, lambda equals 0, in fact, what you can show rigorously is that if you calculate the free energy for this theory on S3 cross S1, you will find that for T less than Tc, the free energy is 3 over 16 n squared, exactly as what is computed from gravity. For T slightly greater than Tc, you find that the free energy, by just doing that computation, nothing more. So this is free gauge theory, right? So it gives you 3 over 16 minus some number, T minus TH, actually T minus TC. And this TC is both a deconfinement temperature and it's also a Hagedorn temperature for all the reasons that we have talked about. So this is what people often refer to as the Hagedorn deconfinement. So the point is that this deconfinement transition is driven by the Hagedorn growth of states. And so in this theory, in the free limit, the Hagedorn and deconfinement transitions happen to coincide. But that's just an artifact of being in the free limit. But the lesson to take from here is that there are some gross features of large N gauge theories and their phase diagram and what kind of phase they are in that seem to interpolate between weak and strong coupling. That's the main lesson. So I will now I will stop being quantitative and I'll just kind of now sketch some more results. So you can ask, so this was all